Tell you 5 minutes before the quindi taglio la descrizione. Barba. Test, test. Devo premere?
È acceso. Sì, ma i volumi.
Ok. Test, test. Test. Doesn't seem to be working. Pronto? Test. Okay. Now it's working. Okay. So we can resume about region selection classification. So is from Christopher Carroll, agent caption selection bias in LSST. Thanks.
All right. Good afternoon. For anyone who doesn't know me, I'm Christopher Carroll. I am an LSST Discovery Alliance Catalyst Fellow, which means that I am one of the very privileged few that gets direct funding to do LSST research. I believe the Discovery Alliance is looking for additional funding for the next cohort of fellows. So if you are a postdoc or a senior graduate student and you're interested in getting paid to do research, you can come talk to me. I'd be more than happy. By the way, these are my presenter notes. I'm not texting. Sorry. Okay. So it's immediately after lunch and we're kind of half sitting in the dark. So maybe you'll fall asleep, and if you do, don't worry. They're recorded, and I probably couldn't see from here anyway. But I just wanted to give special thanks to the organizers of this meeting and the Asian Science Collaboration for the chance to briefly review what I've been working on this last few months. From the title, you can see that we're interested in AGN detections and understanding something of our selection bias, what inherent observational biases there might be, along with our selection effects. This morning, you heard some very similar talk a lot of work by the Italian in-kind contribution work by Ake Vitanen, presented by Angela Bongiorno. I was in Rome last week and I ran into Ake and I said, I'm so excited to talk to you, this week during the conference. And he said, hey man, I'm going to the community workshop in California. So he made me promise that I would talk to Angela if you wouldn't mind. Okay, so our motivations for this. In essence, we are also trying to create mock catalogs, but unlike Agile, which uses very realistic, empirical evidence approach, our approach is more so what if. Okay, what if the universe is not exactly as we can test any prescription of the universe. What if it doesn't follow exactly a quasar luminosity function as we've seen, or galaxies? What we can find outliers using this method. Essentially, we can create a universe at random, and we want to see what will we detect with these sources, and then from there we can begin to understand the selection biases as they come through. Analytical methods are used a lot of the times to understand something about like the number of observations that we will see, the number of galaxies. Like LSST is something like 10 to the 10 galaxies that it will find over its 10-year survey. But what we really are interested in is more so the fraction of these sources that we will detect given the numbers, which is why we're using simulations rather than doing something analytic. We want to actually create these objects. We want to create them in SED, their SEDs, and then see what we will observe and then go from there. So the main goal is to be able to test different prescriptions of the universe. Our aim is to create something that's very fast, very flexible, simple to use for the user. And then our method is to create these mock catalogs using SEDs from the rest frame to the observed frame, and then see what we get. Our ultimate goal are these three things. And so let's dive in to our choices. So, as I said, we want to study AGN. This framework can be at random. Every single parameter, every single black hole mass, everything could be random. And that's the goal. When I say simple to use, flexible and fast, you want to use different SCDs. You want to use a different survey. You want to use a different way to simulate your black holes in your galaxies. So what I'm going to show you now is just one way, right? So before you go, that doesn't look right, just remember this is a single prescription, a single method that we're going to use, just to make sure this works. This is kind of in the beginning stages of this project. So we want to study AGN, so I decided that we're going to start with AGN. So the first thing we're going to do is we're going to take an AGN at redshift and draw from the Shen 2020 quasar luminosity function, which slice at redshift 1 can be seen up here. From this, we'll draw an AGN luminosity. With redshift and luminosity, then we make a choice of Eddington ratio, which leads us to being able to estimate the black hole mass. From that, we use the Rhines involuntary local relation between galaxy stellar mass and black hole mass in order to understand, to estimate the galaxy mass. A paper recently came out, I think it was in March, that creates, that looks at the correction fraction, or the correction factor, the fact that we see an overdensity of higher mass black holes at higher redshifts. So we add this in as well. From this, then we have these two. From that, we use mass to light ratio to estimate the luminosity of the galaxy, and put these things all together into a single source. We put it at redshift. We normalize it to the luminosity that we want. We bring it into the observed frame, and then we slap it with LSST filters, and what we get. For this, we are using the low resolution SED templates by Roberto Asif. Again, it's flexible if you decide that. So the Asif template is one AGN template for both the torus and disk. If you decide that you want to use two component, like this, what we're building is easy, that you can just drop it in, it cranks, and you shouldn't have to do too much work in the back end. So here's just a couple example sources. These are all, I believe, at the same redshift, redshift 2, but with increasing AGN luminosity as you go. The AGN template is, of course, in the purple, and you have a passive, a star forming, and an irregular template that are normalized relative given our mass to light ratio. This is our choice for this prescription. So as you can see, then after convolving with the LSST band passes, we can begin to understand, like, do they pass the limiting depths of the survey in single and co-added 10-year survey. Yeah, for this, we're going to follow the quasar luminosity function. The Shen luminosity function goes from redshift to 7. And so what I'm going to show you in the next slide is a full mock catalog of sorts that will show just slices in redshift 1, 2, 3, 4, but binned in luminosity. Okay. So the first thing we want to know is, will these objects be bright enough that LSST can detect? Okay. So this is the part where I said, don't point and say, that's not how it should be. This is an idealized case. Okay. This is assuming that we are on sky every night. There is no downtime for the telescope. There's no bad weather. There are no malfunctions. There's nothing intervening in the way of the source and the telescope. There's no Lyman forest, right? This is the idealized case. If these things exist, would we detect them in single visit left and the full 10-year survey on the right? So again, in redshift space on the y-axis and luminosity on the x-axis. Just for reference, the single visit and 10-year survey depths are from the science book are below. So the first thing we notice is that, of course, after 10 years of the survey, we get a lot more sources, and we can even start getting into the range here of the really low luminosity sources that recent work have been picking out of. It's the Stripe 82 survey. We will be able to find, in an idealized case, somewhere like 30% of these sources. As you go to higher AGN luminosity, or sorry, higher luminosities, you will of course be able to detect these things in this idealized case, all the way to the highest redshifts. But talk in a slide or two about future work and things that we want to implement so that we can go from this idealized case to a more realistic, but still testing these prescriptions. So after making sure that these things can be detected in at least one of these filters, we add an AGN selection criteria. Here we've just made a simple color selection, U minus G, G minus R, to try and tease out some of the type 1 brighter objects. So this is match, is it detected? Is it selected? The single visit course, shows LS. The 10-year survey is giving us more hope in how many we'll be able to detect. Again, this is the total fraction of objects that are at this redshift in this luminosity range. And given that this gets very close to the upper end, we're more likely to detect these the full sample of these objects, or the full range. When you look at something like this, something that's also important is that each of these squares, these bins in luminosity and redshift, right? This was saying, is it at least detected in one filter, because we can do follow-up observations. You can also take this and look at this per filter. That would be a lot of squares, so I'm not showing that here. But you can do things like simulating dropout objects, like we saw 2 slides ago, or 2 talks ago. So from here, there are a couple of things we'd like to implement, and so in the next slide, future work, kind of also conclusions. But so what we have after this, after running, as many, you choose the number of objects you want, it will give you the total fraction of objects you'll see. This prescription particular was an AGN to galaxy, how you build your source. We also should be able to build the galaxy and seed the AGN. We also should be able to have non-active galaxies and stars. If you want to actually be able to test your selection criteria, you need to add things that you don't want so that you can remove them. Choice of the seeding mechanism, right? So for this, we decided, for this example, I decided, okay, using a mass to light ratio to normalize the stellar components of the galaxy, okay? But what if we want to instead use DP0 to grab, a color magnitude for a huge swath of galaxies in DP0, and use that as a sort of luminosity function for the galaxies. Things like this. Adding AGN variability, and the one near and dear to my heart, AGN obscuration, which if you love obscured AGN like I do, well, anyway, a lot of these things already exist, but we have not tested them, especially AGN obscuration. But AGN variability is a really crucial step, because not only with this method you can see detections per filter for all of these objects. So adding AGN variability might be able to help us discover, rather than just simple color cuts, other objects aside from the brightest type 1 AGN. More importantly is after doing this, is using OpSim to simulate light curves, okay? And then also built in is, weather information, right? Sky time. And so being able to have our, 5 sigma ring depths, modified for loss of observation for the 10-year survey. From this, we can take the bolometric quasar luminosity function of Shen, we can simulate a bunch of objects in the description that you want, and then we can create what we would say is the observed luminosity function that LSST might give us. Also, trying to determine a better LSST color selection criteria than just the ones possibly, to find the biggest and brightest type ones. If I'll leave here, in my tour in Rome, they said that the people were happy, then it was a good emperor. So I would like to crowdsource. What would you like to see? Because if we can keep you happy, then this gets used, and yeah, it's useful. But there is so much different work going on here, and if any of this sounds like this could be interesting, or have you thought, or you'd like to see a particular something be added, it's very flexible. It's also my learning Python, which has been really interesting. Decided I won't do IDL anymore. So yeah, let me know if there's anything else you'd like to see. Thank you.
It's after lunch, so okay. It's a slow pace. So this is, you do a complementary approach of what Angela is doing. In some aspect they look to overlap somewhat. In other things, you're operating differently. And specifically for the light curves, do you have any idea how you're going to implement them? Do you need to rely on a prescription, or there's?
Yeah, so this is one of the things, and I said, hey, Aka, I can't wait till we talk after after a meeting on Monday. But there is no one approach. I would like to have things be flexible enough that the user, right? The idea now is there's one input file, you decide which one you want, and it will go and do this. We can implement multiple variability approaches, especially given the mass of the black hole. There's not one in particular I have in mind. I plan to implement multiple of all these things, and the user gets to choose.
Hi, Chris. Because this is so flexible. Practical use case of this approach might be providing the library of the selection function in terms of z-axis versus the volumetric luminosity. If you marginalize everything, for example, like the different galaxy types and SCDs and everything, do you think we could come up with some sort of the good selection function in the redshift and the volumetric luminosity domain, which practically could be useful when the LSS data comes, and people just construct the luminosity function by taking that selection factor into account? I'm just thinking, how practically it will be useful in this approach. Do you think it's that marginalization actually introduces the more and the wider, the how should I say? Is it really useful by marginalizing everything, or is it a marginalizing everything as make things worse?
So I think the answer to this question is kind of two things, because the reason why we can marginalize over everything is because we want to see, given a prescription, what will LSST look like, right? Which is why you can choose. And then when data comes, or when we have images from the Italian in-kind contribution, we can begin to match, right? I have to think about that. Yeah. Yeah. The one of the goals is to create an AGN selection function for LSST. And there was a talk earlier today also looking to do this. Working together, collaborating on these things is we hope to use this method on things to see if we get the same as other groups as well.
Thank you. I think we have to move forward. Thank you, the speaker again. And now we have Shenli Tang, who's talking about capturing quasar mergers from HSC to LSST.
Hello. Okay. I use this to move. Okay. Okay. Hello, everyone. I'm Shenli Tang, a postdoc from University of Southampton, and I just joined this collaboration at the beginning of this year. So this is my first time to join this offline conference, and it's really nice to see all of you in person. So in this presentation, I would like to talk about the research that I've done during my PhD period to capturing quasar mergers in super HSC and looking into the future of LSST on what we can probably do. So just a quick mention that the HSC Hyper Superm Cam is a camera mounted on the 8-meter Subaru telescope at Mauna Kea Observatory, and this is basically instruments have a similar functionality as the LSST as a survey instrument, and it has done a 7 years sky survey to take the images of 1,300 square degrees in GRIZ Wi-Fi bands. So unfortunately, I haven't been to either of these two, but hopefully I could be one of them in the next few years, and I can put my photo. So what is the motivation? Why are we interested in the mergers of quasars? So here's a very traditional famous diagram of the connections between the galaxies and the quasars. So this suggested that the quasars are formed at the final stage of mergers, of galaxy mergers, when the black holes coalesce and form a bright quasar at the end. So we would know how many percent of quasars are exactly following this kind of evolutional trace. And we would like to compare the merger fraction of the quasars to those of inactive galaxies to see if they are really preferentially formed in this way. So if that is true, this is what we expected. If you compare the merger fraction of AGNs and those of comparison galaxies, you should see an offset between these two populations. But the reality is the merger fraction of the AGNs depends on a lot of things, including the physical properties of the quasars. For example, this tourist et al. 2012 paper shows that for the brighter quasars, they are more likely to be formed in mergers, but for the fainter AGNs, they're not. And also, it depends on the selection, whether your agents are selected by X-ray or optical infrared. So these different colored dots are by different selections. So selection also matters to the merger fraction of your agents. And also the redshift of the quasar. So at high redshift, whether the merger ratio will be higher or lower. And also, there's a more fundamental question is, how do we define a merger? What is a merger? So everyone could have their own. So that motivates us to use a parameter called asymmetry to find the mergers of quasars. So what is asymmetry? Let's say you want to know whether your cat looks symmetric or not. So what probably you will do is you flip the image of a cat by 180 degrees, then you subtract it from the original state of your cat. Then what you get is something like this. This just looks more or less symmetric for your cat, but sometimes your cat doesn't look like this. Maybe it looks like something like this. Then if you do the subtraction, you get the residual image like this. Then you realize something abnormal happened, something weird happened with your cat. So what we are going to do with the quasars to look for the merger exactly similar to these things. We would like to find some peculiar galaxies, peculiar structures. But there's a little bit difference. So what I showed is a kind of the mirror symmetry of the cat, which means, for example, if you flip your right hand with 180 degrees, and then it matches with your left hand. So that is also called charity in quantum field theory. But in the case of galaxy, the symmetry is actual symmetry, which means it's kind of rotating. If you rotate your hand by 180 degrees, it doesn't match with your another hand because your hand doesn't have axial symmetry. But for the galaxies, the interesting thing is that if a galaxy is under steady force, or we say it's dominated by its self-gravity, then it will very likely have even axial asymmetry. So what does that mean? For example, for a spiral galaxy, you will usually see it has 2 or 4 spiral arms, but you seldom see like 3 spiral arms or 5 spiral arms. So that's what it means with even axial symmetry. So if you rotate the galaxy by 180 degrees, it will match with its original shape if it has like 2 spiral arms, or if it is a elliptical galaxy, then also it's kind of axial symmetry. So based on that answers, this is a definition of the asymmetry of a galaxy image. Now let's say you have an image of a galaxy, then you first rotate it by 180 degrees and subtract it from its original image, then you get the residual image of this galaxy. Then you normalize this residual image by the flux of your original galaxy image, then you get a value between 0 and 1. Then this is defined as the asymmetry value. So you can see that this is a non-parametric way of characterizing a galaxy. It doesn't depend on any models that you have known, but only depends on the flux of the image that you get from your telescope. So how do we know this really has any physical meanings? So this is presented in Christopher Consuler's paper in the year of 2000. So on the y-axis, you have the color of the galaxies, different types of galaxies shown in different mark size label here. And the x-axis is asymmetric value between 0 and 1. So typically, you'll find the spheroids or the elliptical galaxies have asymmetric value close to 0. They're quite symmetric. And you'll find some spiral galaxies or disky galaxies have a symmetry value between 0.1 or 0.2. And then the irregular galaxies or some starburst galaxies or mergers will have larger asymmetry value, like above 0.3 or something. So exactly what creates the asymmetry in your galaxy, I summarized it as 2 points. One is the short time scale randomness. For example, the star forming activities or supernovae activities, they happen like randomly over the galaxies, but not necessarily to be symmetric. That creates kind of asymmetry in your galaxy. And the second is external effect. For example, if there's another galaxy coming in, interacting with your galaxy, then you'll find the asymmetric value will be much larger than those kind of isolated galaxies. So it is suggested that we can very simply use asymmetric value. If this value is larger than 0.35, you can say that galaxy is likely merger. So this method, the main advantage is that it is objective. So it doesn't depend on like the subjective intuition of the person that does the classification, and it is simple, just this value, and this is reproducible and extensive. This is very important in the large data era with LSST because you don't want to visually classify the galaxy mergers of like billions of galaxies. It will cost you a whole lifetime. And also this value can be used for the machine learning techniques to classify galaxies. For example, the random forest method can taking this parameter as one of the input. Okay, so here on the right, I'm showing a list of the studies that have been using this method to classify mergers of type 1 quasars. And I hope that, and also there are some studies using visual classifications and some of studies using both of these two methods to classify mergers. And I hope this could give you some confidence to believe that this method somehow works. And what we have done with HST is we have selected like 2,400 type 1 agents from the cross-match area between SDSS and HSC. And we carried out the asymmetry measurement in all 5 bands between redshift 0.2 to 0.8. So technically, how do we do that? Let's say you have a galaxy image. The point is that if now we are working on the quasar galaxy images, so we have to deal with the contamination of the point source. Because remember that this parameter is normalized by the original flux, the flux of the original galaxy image. So if you do not take away the point source, your value will anyway be close to 0 because the emission is dominated by the symmetric point source at the center. So we have to first do a 2D image modeling of the galaxy image. And for this specific sample, we find there's a 1 point source at the center and 5 companion galaxies at the surrounding field of view. So we model all these components with a point spread function and the statistical profiles. Then we take away the point source from the original image, and we get an image of the galaxy only. Then the next question is, since we are going to measure the symmetry, we have to know which pixels we are interested in to do this kind of measurement. We can't do this whole image together. Otherwise, you anyway will get a larger symmetry value because you have so many things around. So that is what we call the segmentation map. So this is based on the contrast between the pixel values that connecting these two galaxies. And we are using the STEP package to do that. So the segmentation map tells you, it's a binary mask, tells you these white pixels are what we want for the SMBH measurement. It's basically this galaxy and the host galaxy of the quasar. And then we input this segmentation map into a package, a Python package called the statmorph. Then it automatically does the rotation and subtraction and the calculation of the symmetry value for you. Then you might say, okay, but how do you know those two galaxies are at same redshift? How do you know that is not a projected loss? Yes, we do know, but back to the first question I raised in the introduction slide, what we want to know is whether the quasars are preferentially formed in mergers compared to inactive galaxies. So we can still do the relative comparison between the quasars and inactive galaxies. So we selected some control galaxies with at the same redshift and the stellar mass range as our quasars, and we applied this method to estimate the merger fraction of these inactive galaxies to be around 17%, and compare that to the quasars that we have as a function of volumetric luminosity and as a function of redshift. So what we find is that similarly, we find only the brightest quasars are preferentially formed in mergers, like around 10 to the 45 erg per second. So below that, there seems no big difference between the quasars and the galaxies. And this is similar to what was found in Trist et al. 2012 paper, also showing that above this volumetric luminosity range, the quasars are more likely to be formed in mergers. But another point is that from our results, we see that the quasars are not likely to be 100% formed in mergers. So there should be other processes that are feeding these quasars, like the secular accretion or other minor mergers, or I don't know. But they are not necessary from the bimerger. But this is a little bit different from the Trist predictions of 100%, but it could also be a problem of the selection of the quasars, whether it is selected by X-ray or infrared optical. And also, we did this for all 5 bands. And if we compare the results from different bands, the purple, green, and blue are from GRI band, and the red ones are from the Z and Y band, we will see a difference between these two. And this is also one thing we have to take care when applying this method to the LSST data in different multiple bands. So from HST to LSST, what we get in the future, or what will be improved with the new data? So a comparison between the magnitudes, the depth, 5 sigma depth of the wide field image of HSC is 26.5, and the deep image is 27.4. For the LSST, the single visit depth is shallower than wide field image from HSC. I think it might take 3 years to catch up with this magnitude. And while after 10 years of observations, the final collided depth is similar to the deep images of HSC. So how would like 1 magnitude depth would help us to understand the morphology of the galaxies? So this is an example of wide image, HSC wide image of a redshift 0.7 quasar that another postdoc at University of Southampton and me are co-supervising a 30-year undergraduate student doing this kind of decomposition work on the wide image and deep images of HSC. So as a comparison between the wide image and deep image, you can see from the third panel, which is after subtracting the point source, you really start to see the host galaxy of a redshift 0.7 quasar with a deep image. So that is a difference of 1 magnitude. So what you would expect to improve from HST to LSST would be something like this. And this is really essential to help us to understand the morphology of the galaxy. And of course, the coverage of the sky area will be significantly improved by LSST by I don't know how many times of that. But so I think the next step will be, I really want to do this test on the agile simulation data, and this will help us to understand the effectiveness and precision of finding mergers with this method. So just final minutes, I would like to quickly mention some spatial phases of a merger as also as a connection to the next session of supermassive black hole binaries. So in the mergers, there's a spatial phases when both of the supermassive black holes could be activated simultaneously and form a dual quasar. And these kind of systems are discoverable with single epoch image. So this could be done in parallel with the search of quasar galaxy mergers. And this is actually we are pointing at a different parameter space as a supermassive black hole binaries because pure quasars are defined as like a quasar pair with hundreds of things in kiloparsec scale separation. So not really the final state of merger, but you can still see separate the two galaxies. And in these phases, the interesting point is that you can trace the behavior of the supermassive black holes in the galaxy mergers. Okay, quickly go through these. These are some candidates that we have from HSC, and we have done some spectroscopic confirmation of these systems. And in some cases, we do find broad emission at both sources, and they are well separated. And their line ratios are different, so that they are not length quasars, but really physically associated quasars. And this is the parameter space we're pointing with HSC, and with LSST, I think the parameter space will be quite similar to this, between 0.6 arcsecond to 4 arcsecond. Which is the separation between the two nuclei of the quasar pairs, and which corresponding to around 10 to 20 kiloparsec separation between the redshift 0.5 to 3 or even above. Okay, so it's okay. Finally, I just give my summary here that mainly I would actually introduce the symmetry parameter, which is a simple and reproducible and extensive classifier of galaxy mergers. But we needed to take care of the point source, and this is the tricky point of the pipeline. And among those galaxy mergers, there are spatial phases when both of the quasars are activated. They are called dual quasars, and they're really interesting to follow up to study the behavior of the supermassive black holes in galaxy mergers. And the paper is available with a QR code for the asymmetry study. And thank you for listening.
So first question is, how do you subtract the quasar? You just use a points per function from the HSC catalog?
Function at every sky coordinate. So it has a model at everywhere. You just give a coordinate of it, then it will give you a model of PSF.
So the points per function from the HSC database is not perfect. So I have to use the model to model the points per function for my personal use, and that can improve the fit a lot. Yeah, but we can discuss about that. Yeah.
Okay, right. Thank you. Marcy?
Thank you, Shen. It's really interesting. I didn't fully understand why you see different merger fractions in different bands. Is that because galaxies are more asymmetric at shorter wavelengths, or is that because the signal to noise is better?
So, yeah, as you say, that in different bands, the depths of the images are different. So, in some cases, the secondary galaxy is resolved, like in I band, because you have the deeper image of that. That's right. Don't have a backup. But maybe in Y band, also because of the sky background, and also the depth is like 1 magnitude shallower than I band, then you cannot resolve the secondary galaxy, then you missed it. Oh, yeah. So what we find is like in bluer bands, we usually have a higher merger fraction. That is also probably because of the stellar population we're pointing at. So maybe most of these mergers like have star forming activities. So you have more younger stars, but those younger stars are not seen in the red bands. So that's why when you try to make the segmentation map of your galaxy, you'll miss those kind of stellar population. You miss those pixels, and that makes your symmetry value is lower. So, yeah, this is kind of very tricky point. So a lot of facts are in situation.
It's a very quick question, very interesting. I was wondering like how you account for obscuration, because we know that most Stagian emergers are obscure, right? And this can create a lot of biases, particularly at low luminosities.
Yeah. So for this sample we are studying, they are all like checkpoint agents, so there are no obscuration. I mean, they are unobscured quasars because they are SDSS quasars.
Yeah, but in general, I mean, you want to have a complete view, right, of things. So, I mean, you're probably missing a huge fraction of objects that are not type ones.
That is kind of our next work is to use the X-ray studies, use the X-ray agent catalog to do a similar stuff and to include those obscured cases. Yeah, that's true. So what we can tell from this is like SDSS quasars, they are preferentially formed by mergers if they are bright enough. But as I show in the very beginning, that the merger fraction of the quasars really depend on multiple things, like I don't see the rest what, but the selection, and also the luminosity and the redshift. Thank you.
So let's thank the speaker again. And okay, so we
See? Okay, so we have to come back with our feet on the ground. And the first speaker of this session is Maria Carisi, that will talk us about research of supermassive black holes in the LSST era. Please.
How do we make the slide? Oops. Shall I wait for the slides? Okay. Well, it's hard to follow the projection. I'll do my best. First of all, thanks to the organizers for inviting me. As you heard, I'm going to talk about searching for supermassive black hole binaries. And my ambitious goal, thank you, is to cover both photometric searches with LSST, but also the synergies with gravitational wave observatories. Of course, as we know, supermassive black hole binaries should form very frequently in galaxy mergers, since every massive galaxy has a supermassive black hole. This was supposed to be a video, but of course, we know that every massive galaxy has a supermassive black hole in the center, and the galaxies merge through the history of the universe to build up more massive galaxies. So that process naturally makes galaxies that have two supermassive black holes in the center. And in the post-merger galaxy, the two black holes evolve and move to smaller and smaller separations. And the stage that I will refer to as binary is when the two black holes become gravitationally bound. So it's the final stage of this galaxy merger. The important part for us is that galaxy mergers typically involve a lot of gas. That gas can be funneled in the central regions of the post-merger galaxy. They can accrete onto the two black holes and provide great electromagnetic signatures, which of course allow us to detect these systems. And there has been a long-standing problem in galaxy mergers and galaxy evolution on how these two black holes get to the final stages and merge. And the very basic steps of evolution have been known for almost 50 years now. So initially we have the two black holes sinking to the common gravitational potential through technical friction. This process is efficient up to a few parsec. Then we have interactions with the immediate environment, either three-body interactions with stars or with the gas that I already said must be there. And these processes can catalyze the binary evolution, and eventually we have the emission of gravitational waves and the final coalescence. So for a very long time, this intermediate step has remained uncertain, which is the well-known final parsec problem. And one of the reasons is that in this regime, we don't have observational evidence for these binaries. So we have never observed a binary with a separation less than a parsec. Now, let's see the overview of where we are observationally. Very often we see the initial stages of galaxy mergers. And in the last 2 decades, we have seen a few dozens of post-merger galaxies that have two active supermassive black holes separated by kiloparsec distances. And these are relatively easy to resolve. And we call them 12 AGN. Now, if we go to smaller and smaller separations, taking an image of a galaxy and seeing the two black holes becomes more and more challenging. So when they are at the parsec scale, we need very long baseline interferometry to resolve the two black holes. So practically using the entire Earth as a telescope. And this system here that has a projected separation of 7 parsec is the record holding binary. So if we go to even smaller separations, then we really don't have the resolution to detect these binaries. So we need to infer the presence of the binary from the effect they have in their environment. And one of the very promising methods is to find quasars that have periodic variability. So why quasars first? We think that at least some of the quasars are activated by galaxy mergers, as we heard in the previous talk. So it makes sense to look in these galaxies to find two supermassive black holes. Now, why periodic variability? Again, I would say this is fairly intuitive since we have a binary that is periodically perturbed in its environment. But again, this has been confirmed over and over in simulation. So when we put two black holes in a gaseous disk, the binary acts as a propeller. It removes the gas from the center and it creates a low density cavity. But this system is dynamic and we have streams of material that penetrate the cavity and hit the black holes. And we also have these mini disks of material that get bound to the individual black holes. So we have two main methods, and I will mention one more in a few slides, to produce this periodic variability. One is, if you look at the accretion rate to the binary, we see that it's periodically modulated. So the second one has to do with this gas that gets bound into the individual black holes, and it moves with relativistic velocities. So this signature is more prominent if the binary orbit is not far from edge on, and also if we have a relatively unequal mass binary. So if we have an unequal mass binary, typically the secondary black hole, the small one, has a brighter mini disk that dominates the variability, and it's also the one that is moving faster. So when the secondary black hole moves towards the observer, it will appear brighter. When it's moving away, it will appear dimmer, and that gives rise to this sinusoidal periodicity if the orbit is circular. Now, we've seen this slide before, this compilation of time domain surveys. And in fact, in the last, let's say, 10 years, we had a lot of developments in this field because for the first time, we had big samples of quasars that we could analyze their light curves in search for periodicity. And in fact, by now, we have analyzed most of the time domain data, existing ones, and we have found quite a few candidates. So we are in the era of candidates. These are just a few examples of these 250 candidates. And the emphasis here is on the word candidates because finding periodicity in quasars, as you can imagine, is very challenging. A few of the reasons you can see them, we have periods that are very long, so we cannot see many repetitions of the periodicity. We have, as always, sparse data, and another reason is less obvious, but I'm sure it's pretty obvious to this community, is that quasars have stochastic variability that can mimic the periodicity. So this is one of the example light curves that we have detected periodicity in the points, and in the back, the pink line is a simulated quasar curve that has a single supermassive black hole. And you can see that in the limit of these few data, it's almost impossible to differentiate the periodicity from the stochastic variability. So quasar variability can mimic periodicity. Another, I think, less appreciated fact is that it can also hinder the detection of real periodicity, and I will get back to this in a bit. So we need to have better noise model to do better statistics. Weizhang, for example, has already a better model to describe quasar variability, but as we move to LSST, I think this will become very important. Now, one of the good things is that if it is indeed a binary, it will have persistent periodicity. So if we look long enough, the periodicity should stay in the data. And if I go back for a couple of slides, I had an asterisk here because when this paper came out a couple of years ago, it had about 100 and something quasars as binary candidates. In the final version of the paper, they extended the baselines with historical data. The initial search was CTF. They used PDF and Catalina and other time domain surveys. So of the 127, only 3 have persistent periodicity, which are the 3 here. So the good news is that if we observe long enough, we can really differentiate the two scenarios. Bad news is we need long baseline light curves. So this is something I've been thinking and I wanted to bring up to this community. When LSST will start, we will have very short baselines. And for the search of binaries, it's very important to combine with previous or currently ongoing time domain surveys. So if you're thinking about this, come talk to me because for us, at least for the search of binaries, this is very important. Now, this is the third method that I already promised for producing periodic variability. This model produces periodic flares. So we have a binary here, and at some point, one of the black holes and the accretion disk of one of the black holes will go behind the other black hole, and that produces a self-lensing flare, which can be detected as something very prominent, like this one. So this is, again, a binary candidate that was found quite serendipitously, because not because it has a repeating flare, but because the flare it has, this AGN is from Kepler, it's very symmetric. And as far as we know, it's this self-lensing model is the only model that produces such a very symmetric flare. Now, people have looked at how many self-lensing flares we should expect with LSST, and it turns out that this is in the hundreds, if not in the thousands. One comment on this is that the rolling cadence is not very, very helpful for finding these persistent periodicities, but for finding the self-cleansing flares, it actually helps a lot. So there's also a trade-off in finding binaries. With Ilsan here and a few other people, we have started thinking on how to simulate flares and periodicity, periodic signals like this, and test how well we are doing in detecting these with LSST. Now, an additional approach, instead of waiting years and years to see if the periodicity is persistent, is to look for additional signatures. So the binary, I guess, can affect the jets. If there is a jet attached to one of the black holes, it will be moving around. So we expect helical jets. It will affect the spectra. Again, if there's a broad line region attached to one of the black holes, since it has a systematic motion, it will appear as the Doppler shift in the lines. Maybe we should see astrometric shifts in VLBI, and of course, we should see gravitational waves at some point. So here is a compilation of the different signals that one can look for. And if you're interested, there is a very extensive review on the potential signatures and all the observational efforts to find binaries in recent years. But I would say the bottom line is that there are some candidates that have multiple lines of evidence that there is a binary in that candidate quasar, but its signature is not unique. So even the typical single supermassive black hole quasar can have similar behavior. So it's hard to distinguish the binaries from the normal population. Now, of course, we're very excited for LSST because the main thing is LSST will find many, many more quasars than what we have now. So the biggest of these photometric sets analyzed about 100,000 quasars. But with LSST, we're getting to the millions. And in such big samples, we also expect to find the more rare short period binaries. So for example, you can see here, this is a theoretical prediction of how many binaries we should expect with, let's say, a period of a month or 2 months. And these are the numbers here. So we expect thousands of binaries. And if we have a binary with a period of 2 months over the course of the 10-year survey, we will have many repetitions, many cycles. So we won't have any doubt that this is the noise that is causing random fluctuation. So I would argue that the soft spot for binary detection will be these short period binaries. But in preparation for LSSD, we also developed a method to select periodicity on top of realistic quasar noise. And we tested it with simulated data. And what I'm showing is an ROC curve, so the true positive rate, real signal that should be detected, versus a false positive rate, so noise that is falsely identified. If our selection was random, it would be this line. If it was perfect, it would be something like that. And we tested it with data that look like Catalina, and what we expect for LSST. I have to admit, this is a highly idealized LSST version. So Caitlin is working to update this figure with a more realistic rolling cadence. But what you can see is this is the detection threshold here. We have about 60% of signals being detected in both cases. So only due to the fact that we have this drastic red noise, we miss a lot of the signals. If we just had white noise, we would find everything. Now, the other important thing is if we go from something like Catalina to LSST, we go from 20% detection rate to something close to zero. And the reason for that was the quality of the LSST data. Of course, this is a Bayesian model selection. It's quite computationally expensive, so we cannot apply it to the entire LSST database. Now, if we look a closer look at which binaries we can find easily and which are harder in terms of the injected parameters and the recovery rate, the trends are similar. The shorter period binaries are much easier to find than the longer period binaries because we have many more cycles within the baselines. If we have higher amplitudes, strong signals, again, it's easier to detect them. If we look at the noise parameters, we lose many more binaries as the noise becomes stronger. So this sigma parameter is somewhat like the amplitude of the noise. So there's no surprises here. It's easier to find stronger signals. And if Megan was here, see with a different method, we kind of found the same result. Now, for the last 3 or 4 minutes, I'll try to describe the potential synergies with pulsar timing arrays. So the half-point introduction to pulsar timing arrays is that PTAs are a galactic scaling detector that relies on pulsars, which are very precise clocks. And the goal is to find coherent deviations in the arrival time of pulsars due to the passing of gravitational waves which stretch and squeeze the space-time between the pulsars and the Earth. And as of last year, all major PTAs collaborations have announced that they have found evidence of gravitational wave background, which is likely produced from supermassive black hole binaries. So we have a project to predict how many binaries LSST should see based on this background, but I'm not going to talk about this. The more exciting aspect is that in a few years, we should find individually resolved binaries that stand above the background. And these sources, we catch them a very long time before the merger, and they're practically monochromatic sources. So they emit gravitational waves at a single frequency. And of course, they're very promising sources for low frequency multi-messenger observations because, as I said, binaries should also produce bright electromagnetic emission. Now, gravitational waves probe the orbit, electromagnetic waves probe the conditions of the plasma and the interaction with the binary. So it makes sense to combine them and get the most complete picture of the binaries. That's why multi-messenger is interesting. And there are two main ways to get to multi-messenger detections. And I'll try very briefly to tell you how LSST can contribute to this. One is find gravitational waves and then find the associated electromagnetic counterpart and find the host galaxy. And the second possibility is find electromagnetic candidates, like the one I already told you, or the ones that the LSST will find. And then do a targeted search to find gravitational waves from the same system with consistent parameters. Now, in the second approach, it really increases the sensitivity of the PTA search. So if we know where we are looking, it can help a lot. So this is a detection statistic for different scenarios for the same binary. So typically we do a completely uninformed all sky search, but if we know at which galaxy to search, or we have some information about the mass or the period, we can go from a very uninteresting, let's say, subthreshold binary to something that is very important. Of course, we don't really know what happens if we are targeting false positives. And since we expect that we have a lot of false positives, I would say that there's still a lot of work needed here to understand what happens if we target a false positive. Now, the good news is that the time domain surveys and pulsar time-in-arrays have very good overlap in terms of parameter space. And this is the total mass of the binary and the period. And the blue shaded region shows binaries that can be detected with electromagnetic waves, and the purple with PTAs, assuming different sensitivities, starting from the nanograph 11-year dataset, going to something like what we have today and projected in the future. So what we what we can do currently is detect the most massive binaries. But as the sensitivity of PTAs increases, more and more binaries enter this common parameter space. Now I'll skip a few of those, and I will say that if we analyze jointly electromagnetic waves, light curves, and gravitational waves, we get much better parameter constraints because we break generacies that have the different, each signal has different dependencies on the parameters, and if we analyze them together, we can really tighten the parameter constraints. Now, do we have 1 minute? For the last 1 minute, I want to describe the other approach, which is to find gravitational waves first, and this work we did with Paulina Petro. So what we did is we took a galaxy catalog, a real galaxy catalog from this paper, and we injected binaries. And then we simulated the end-to-end discovery process of gravitational waves, the localization, and then we used the catalog and to find which galaxies could be in that area. And here I'm showing a few of the examples. You can see that the localization is several hundreds of square degrees, so they're big parts of the sky. But if we do one more step and do cuts based on the mass and the distance of the binary, so we can get down to a few hundred possible hosts. So even though we get a very big localization area, because PTAs are sensitive to the most massive galaxies, which are we can reduce the number of potential hosts. And hopefully LSST can also help us with that by finding electromagnetic counterparts, and in particular, finding quasars or AGN with periodic variability. For the last slide, I just have a few challenges or opportunities for the future. I already mentioned a few of those during the talk. So one of the challenges is the baselines. To find binaries, we need many cycles. So hopefully we would benefit a lot from combining the LSST data with existing time domain data. The stochastic noise and how we do the statistics is another huge challenge. So we can either go beyond the dumb random walk. I didn't get to mention this, but we can also use a data-driven approach and the noise agnostic model. So stay tuned. That project with a PhD student at Berkeley will put out on the archive this new method paper this week. And of course, there are other problems like does the rolling cadence help with finding binaries? We have multiband light curves. How do we deal with those? Um, Also, I mentioned a few of the periodic signals, like we have very good analytical descriptions for self-cleansing and Doppler boost, but not all the signals are very well known theoretically. And of course, for finding gravitational waves, the localization will be hard. And another thing I just wanted to mention, because I think there are people here that are thinking about that, maybe in these massive galaxies, we won't have like a quasar point-like source, but we will have a the AGN, which will be an extended source. So if you're also thinking about this, come talk to me, because this would be, I think, very important for finding electromagnetic counterparts. And that's all I have.
Two questions and a comment. Questions, what is the width in time of those flares?
It depends a lot on the parameters of the binary, like the separation, the mass ratio, and things like that. But typically, think of it, it could be from a few days to a few weeks.
That's longer than I thought, just because of looking at the Lie curve, which is good. I mean, but if it was just hours, it's like, oh, when am I going to find it? Okay, the other thing, how much orbital information can you get from the gravitational waves in that kind of thousands of years type of purchase that you were talking about?
Yeah. Right. So we get the frequency. That's the easy thing. And maybe I can go back this that I didn't get to discuss in much detail. So from the gravitational wave, we get the frequency, the total mass of the binary, the constraints, the mass ratio, orbital inclination, and the phase of the gravitational wave, which maybe we can relate it to the phase of the electromagnetic wave. So these are all the parameters that we can constrain gravitational wave alone. Yes, because there's we get the one frequency, but the amplitude depends on many other parameters. Some of them are degenerate between them, but the good thing is that if you look at the electromagnetic signal, it has different dependencies on the parameters. So if you assume, for example, the relativistic Doppler boost, you put them together and then you get very good constraints.
That is not a question, right?
Hi. Apologies if I missed this. Could it be that the stochastic noise is somewhat random in the different filters, whereas the binary signal is the same in different filters? So color information, which we will have, different filters will help us separate whether or not we've got a true binary or just noise.
So it depends on the model we assume for the binary. For example, for the relativistic Doppler boost, there is a very specific prediction that depends on the spectrum of the binary. Now, if you can differentiate that from the noise, we have looked at that in terms of optical and UV variability, because the same can work for optical UV X-rays. It turns out quasars have chromatic variability. They can mimic this signature also. I would say if you have very good quality of data, then it should be easier to differentiate the two. With UV light curves, we had very sparse light curves, so it was very easy to confuse the two signatures by chance.
Okay, if there are no any questions, now we have a coffee break. We reconvene here in about 25 minutes, so for 40. Okay, thanks to Maria. Okay. If you don't have a register already for the social dinner or for the martini visit, you can do it now at the desk. Okay, let's start again with Jorge Cuadra. Quadra, that we talk us about organized milliparsec supermassive binary cut.
Hi, good afternoon. I'm Jorge Cuadra. I'm going to present you a very interesting source that we found that we think it might be a sub-milliparsec binary supermassive black hole, and that we see it because it just accreted or captured a big gas cloud and is disrupting it and accreted it. And I will show you that. I'm presenting this on behalf of a relatively large collaboration led by Lorena Hernandez Garcia. We submitted this paper like 1 month ago, and there's several other members of the collaboration here, Paulina, Patricia, and Paula. So I'm the theoretician here who kind of interprets what we see. If you have any questions on photometry and so on, I will defer you to them. So the source was discovered on the CTF public alert stream. It was found classified by the alert broker. Those things were explained earlier today by Paula. And so it's a source that was found in an already active galaxy, on a Seyfert 1 galaxy, which had a light curve that was very typical of a Seyfert 1 galaxy. So variations, and it was not constant, right? But suddenly it went much, it reached a much higher flux. And since then, I mean, that happened in March 3 years ago. And then it's been going up and down, maybe 7 times or so. And with a sort of periodicity, as you can see here in the light curve. Here it's shown both the G and the R bands of the ZTF, and the peaks occur every 70 days or so. Also, it's interesting that this galaxy has another AGN just 9 kiloparsec away. So, I mean, of course, that other galaxy is completely unrelated to what I will focus on, but it seems that this is an object where we can study the assembly of black holes on different scales. So after the alert, the team started getting data in numerous telescopes. So here again are the G and R light curves from CTF, but also we got data from Swift on the UV and X-rays. And you can see in all of them, there's the same sort of periodicity, very similar behavior. On the other hand, the radio emission, there's apparently no nuclear radio emission. So which kind of source this is? Could be, I mean, quasi-periodic eruptions, which have become, which people have started discovering recently, occur on much shorter timescales. Here we have something like a period of 17 days or so, so it's way too long. And also the spectrum of this source is too hard. Could this be a change in look AGN? Not really, it doesn't fit that kind of source. We see that the optical spectrum has not changed. And also, even though originally it was a Cipher 1 with stochastic variability, now the variability is not stochastic. It shows it clearly shows a preferred timescale. And finally, for the other typical kind of source that we could think of is a tidal disruption event. But the spectrum does not fit at all. I mean, the spectrum is too hard. And also the colors are are very different. And perhaps most importantly, a tidal disruption event would not be expected to show this kind of oscillating light curve. What does produce an oscillating light curve is a binary black hole. So if we, and Maria just described this in her talk, I asked for permission to include the animations, so now you can see the motion of the black holes. And sorry about that. There it is. You can see how the motion of the black holes drives these kind of waves of the material that is in the binary disk. So the black holes are periodically capturing material and forming these streams, and then these streams, again, the binary is colliding with the streams, and accretion proceeds in a very periodic way. So in this case, we have a peak every orbit, but depending on the properties of the binary, so whether it's eccentric or circular, the mass ratio, and so on, you can have a periodicity on twice, 2 times faster than the orbital period. But also you can have a variability on longer timescales. You can see here, for instance, that there's like an overdensity in the circumbinary disk. And in the case of circular binaries, the motion of that overdensity is actually what drives the variability. So you get a per period of like 5 times the orbital period. So you can have, depending on the properties of the system, you can have different preferred periods, but typically they are close to the binary orbit, and you pretty much always find that. The problem with all of this is that our source cannot be fit by this because it was a regular AGN, and suddenly it started oscillating. So it's not like a binary suddenly appeared in the center of a disk. But what if we have a binary that accretes or captures a star? What about a tidal disruption event on a binary, by a binary? That has been modeled. There's a few studies, and here I'm showing you light curves, rather accretion rate curves, done by Villiron and collaborators a few years ago, in which they modeled binaries with different mass ratios and different separations, in which a star was tidally disrupted, and the different curves show also different orientations. So you can have the star coming perpendicular in the same plane. There's a lot of possibilities. And what they found is that typically you get something that resembles a regular tidal disruption event, but in many cases you get interruptions. And those interruptions occur because the stream of material, which is the disrupted star, gets perturbed by the orbit of the secondary black hole. So you get like this envelope, but with dips. And the dips, when the dips occur, depends on the properties of the system, the orientation mostly. And in some cases, it's hard to see here because the time axis is logarithmic, but in some cases, these interruptions occur periodically on the period of the binary orbit. So we were very excited about this possibility until March or so this year, when the source went up again. So none of the, I mean, in all the models that Vigneron and collaborators performed, that behavior was never found, and they covered a lot of parameter space. So it seems that tidal disruption event, even around the binary, does not work. So what's left? what's left is something we had actually modeled almost 10 years ago, when we were not thinking about fitting any particular source at all. And that is, what if we have a binary supermassive black hole, but rather than accreting a star or capturing and disrupting a star, you disrupt a molecular cloud. So, as I said, our motivation was not to fit anything in particular, but simply that we expect molecular clouds, large gas clouds, to exist in galactic nuclei, either because of turbulent motion, compresses the gas and makes clumps, or because there's a lot of gas that becomes self-gravitating. So there's many reasons to expect large clouds in galactic nuclei, some of them getting to the center. And actually, there have been studies, for instance, this one by Bonnell and Rice, that had studied had modeled what happened when you have a cloud falling onto a supermassive black hole, but a single supermassive black hole. This was done in the context of our galactic center, where we see that there's a disk of stars, and the best explanation for that disk of young stars is that they were formed from a gaseous disk that was massive enough to become gravitationally unstable. So we kind of repeated this study, but instead of having a single black hole, we had a supermassive black hole in the center. I'm going to show you a couple of movies of what happens with the cloud for different parameters. So here I'm showing what happens when you have aligned orbits. That means that the binary and the molecular cloud, they are all in the same plane and going in the same direction. You see that if the impact parameter is small, most of the cloud gets either captured by the two black holes forming these mini disks, and the rest gets violently expelled. But if the impact parameter is wider, it's larger, a lot of the material survives in a and will end up forming a circumbinary disk. If you have If you have perpendicular orbits, the dynamics is more complex. It's harder for the black holes to capture material, and you see that there's a lot of the binary drives waves, but accretion still proceeds. And in this case, you can imagine how you can see how the black holes are encountering material all the time. So each black hole once per orbit, so you get a peak in the accretion rate, in the total accretion rate, twice per orbit. So we ran a number of simulations with different impact parameters, different orientations, and unlike the stellar case that was studied by Vigneron et al., in our case, we find a much wider variety of outcomes. So this is the accretion rate onto the black holes from the simulation as a function of time for different parameters. And yeah, in some cases, we see a behavior that resembles what has been observed. So we have a few peaks, then it gets more quiet, and then it goes up again. Now, perhaps this is not the best example, rather this one. A couple of large peaks, smaller peaks, large peaks again. And of course, this is just a handful of simulations. For a gas cloud, the parameter space is huge. You can have different shapes, different density distributions, so on and so forth. Also, we found, going back to the observations of this subject, this is this Carroll magnitude diagram of how it was before the peak and then after the peak. You can see that in general, there's this bluer when brighter behavior, but after the peak, the source is redder. So this very qualitatively agrees with what we would expect. So maybe there's reddening, so the source keeps, we can imagine it would stay with the same behavior, but we see it obscured because of the debris of the cloud that was not captured. So yeah, assuming this is a binary, peaks would occur twice per orbit, so we would have an orbital period of 130 days. From the optical spectrum, there's an estimate of the black hole mass of 40 million solar masses. Putting those numbers together, we would have a separation just below a milliparsec, which is a few hundred Charisi radii, depending on the mass ratio of the binary. So this is rather compact, and and even the distance to this object is half microarc second, which is unfortunate because it's too small to be resolved by gravity or the Event Horizon Telescope even. On the other hand, this compactness means that the binary is smaller than the expected size of the broadline region, so it does make sense that we haven't seen anything weird in the lines. The spectrum has not changed. And because of how close it is, this source should be emitting gravitational waves, and we expect it to merge relatively soon in 7 times 10 to the 4 years. So, I mean, don't wait for it, but it's much sooner than most candidates we could find. So to conclude, we found oscillations on otherwise normal C1 galaxy, none of the usual transients works to explain this source. So we propose that it's a milliparsec binary that capture and is accreting a gas cloud. Given that, and also the fact that there's another galaxy just a few 10 kiloparsec away, this is a very nice source to study the assembly of black holes, and we can expect to have many more interesting sources with the Rubin Observatory. Thanks.
Thank you. Interesting idea. I have 2 questions actually, which are a little related. First of all, I'm curious, in your simulation, what is the mass of the molecular gas cloud you're assuming? And also, do you have the X-ray spectrum, which could potentially suggest if there's any obscuration happening during that transition?
So in the simulation, the mass of the cloud is like 1% of the binary mass. So it's dynamically negligible. It's a large cloud, but 10 to 4 solar masses, something like that. And the X-ray spectrum, I don't think we have. Does anybody want to answer that? Claudio thinks there was not much obscuration. Sorry, I forgot to mention Claudio is also involved.
Question, Jorge. What is the mass ratio of the 2 black holes? And is it still the case in these simulations, as in others I've seen, that it's the smaller of the 2 black holes that does most of the accretion, the higher m dot of the 2?
So in this simulation, the black hole is equal mass ratio, and the accretion rate are pretty symmetric. So you get one gets a peak, the other gets a peak. Now, more in general, it's not always what you say that the secondary gets more accretion. Actually, in the cases when the binary is eccentric and also that makes the cavity of the circumbinary disk also eccentric, and then you have a situation in which the black hole that has the pericenter like aligned with the cavity gets more accretion than the other. Something I'm not sure, something like that. But the point is that they take turns because the binary is making the circumbinary disk precise. So you get long periods in which the secondary accretes the most, but then the primary accretes the most. So you could actually preserve the mass ratio rather than tend to equalize.
I have a question about the state of the source even before the increased variability, because if you have binary black hole and those two 300 gravitational ready, then you don't have the called standard Kurasunayev disk there, right? The accretion process differently, so it should be mostly space, not much in the optical, whatever. So even if it was classified as Seifert 1, it was not probably as standard Seifert 1. So it would be nice to have a closer look even before the outburst at the broadband density.
Well, I don't know. I mean, that sounds like a very good point that we, at least I had not considered. Paulina?
So a good idea to look at the ECT, because the only thing we have it's a spectrum, an old spectrum that unfortunately it has calibration issues. It looks similar to what we see now. As I said, it's not complete.
So you saw the two simulations, and I guess one parameter that was important is where the impact of the cloud is. And in one case, you have persistent periodicity when you form a circumbinary disk, and in the other, I guess, it's the more transient, right? So in case, now that you have a light curve, can you differentiate between these two scenarios and predict how long the periodicity should last?
Yeah, I mean, in principle, one could do that, but I just don't think the parameter space we covered is representative enough. So many different ways in which clouds can be different that, yeah, I mean, there's so much variety there, and you could have, and there's no clear trend either, other than when you go straight the cloud force with a very small impact parameter, it gets destroyed more quickly. So yeah, I wouldn't trust any conclusion. But in principle, it's doable if you have 100 simulations rather than 12.
Okay, thanks, Jorge. The next speaker is Francesco Tombesi with a talk with a very long title.
Okay, let's see. Okay, so you have seen very nice movies and simulations before. I didn't know that I could use movies we have also for our case, but they were really, really inspiring. So basically, I would like to talk to you about a pretty strange case that we started to study about 2 years ago, and we think it is an evidence for a supermassive black hole in a binary orbit with an intermediate mass black hole, and the system was possibly triggered by a TD. Okay, so basically we started from an astrophysical flare in the nucleus of a galaxy. This galaxy was one of those random galaxies at a redshift of about 0.056. This was discovered by Sassin in optical in late December 2020, and it was also seen by the Gaia Space Observatory. You can see here the optical light curve in Assassin and Swift U-boat, and basically there is a rise, a peak, and a decay on about 150 days. And it is broadly consistent with what we expect from a tidal disruption event. Also, the time evolution of the optical UV blackbody temperature and radius, you can see here, during the outburst is rather similar to what people have observed already in TDEs. Okay. So then we triggered a follow-up in optical spectroscopy in order to understand the redshift of the source, and in particular to get to know the environment of this object through optical spectroscopy. And interestingly, what we started to see is that with following the increase in flux, there was also an increase in intensity of hydrogen and oxygen emission lines. So basically, we found evidence that the Broadland region in this object was still dynamically bound to the supermassive black hole, and it was rising in intensity. So basically, a supermassive black hole waking up. From here, we estimated a mass of the central object to be about 10 to the 7.5 solar masses, so a supermassive black hole. We then performed additional tests in order to understand what kind of object we were dealing with. In particular, from the BDP and one diagrams, we got indications that Assassin 20QC is indeed an AGN. So we find evidence that it was a borderline AGN liner, and here, after the detection, we found that it is consistent with a strong AGN activity. We also tracked EROSEED archival data, and so basically before the outburst, we have an upper limit of the luminosity of about 6 times 10 to the 40 arcs per second, which basically indicates that before the detection with an optical outburst, the source was a low luminosity AGN accreting at a very low attitude limit, 0.002%. So a low luminosity AGN, possibly undetectable in optical due to the fact that the host galaxy was dominating. After about 2 months, we detected the source in X-rays with Swift, and then we also triggered a nicer campaign, a high cadence campaign with 1 to 2 observations per day during, just after the peak. We also see a time delay between the X-ray and optical outbursts, which is again consistent with a TDE. And also here you can see the spectrum in the X-rays is consistent with a simple black body with a temperature of about 100 EV. So what is interesting here is that if you look here in detail in the nicer monitoring, you can see that the spectrum, the light curve is not constant. And also, if you do spectroscopy, you can see that there is a continuum level here and possible evidence for an absorption, a broad absorption trough here at the energy of close to 1 keV. So everything happens in the soft X-rays. So then we wanted to see what was going on. So basically, thanks to the nicer data, we performed a study of the ODR, is the outflow deficit ratio. Basically, it is a ratio of the counts in the absorption band and in the continuum band. We saw that the continuum didn't show any significant periodicity. However, if you look here, the ratio between the absorption and the direct continuum, it indeed shows periodic, quasi-periodic variability. And we performed a deeper analysis. So we calculated the Carroll parallelogram, and basically we get that the ratio between the absorption and the continuum shows a quasi-periodicity of 8.3 days with a confidence level higher than 4 sigma through Monte Carlo simulations. So what's changing here is not mostly the continuum, but it's the absorber, the obscuration. We then performed timers of spectroscopy with nicer data, and we looked at the spectra during the peaks and the dips in the ODR curve. So basically, using photoionization codes, we find here is the column density, ionization of the plasma, and velocity. We find that the data are consistent with oxygen 8, mostly, so highly ionized oxygen, with a blue shifted velocity indicating outflow coming from the inner region of this accreting source at about 30% of the speed of light. So what is typically called in the X-rays ultra-fast outflow. The velocity is relative. You see here, ionization changes, but not too much. But what is changing actually is the column density of the absorber. It changes by a factor of 10 and is giving rise to this quasi-periodicity. So we call this phenomenon quasi-periodic outflows, QPOs. I mean, you can come up with more interesting names. And here there were some nice videos, but maybe okay, you can imagine them. So basically, we considered several theoretical models to interpret this evidence. We considered recessing inner disk, clumpy or slow outflow, X-ray reflection, disk instabilities, quasi-periodic eruptions, and repeating partial TDs. All of them were not able to fully explain the observations, except for one, a model in which there is a closed binary system with a perturber on an inclined orbit with respect to the central supermassive black hole. So in this model here, these are numerical simulations. You see the central supermassive black hole. You supply matter through either a cloud, or in this case, we think it's most likely a Terra disruption event. And you start to basically form an accretion disk. And then there is the secondary object that goes through the accretion disk of the primary supermassive black hole, and basically is modulating the outflow, the obscuration at each orbit. Here is another sketch of these GR MHD simulations, and here you can see the simulation with accretion flow. We also check what's happening without including secondary. There were sometimes spurious modulations, but they were lasting only for a few cycles and on very short time. When you include a secondary object with an orbit close to the primary object, you have these modulations, these periodic outflows in the matter which is outflowing vertically from the disk. So basically, we estimated that the secondary object is an intermediate mass black hole with a mass range between 100 to 10,000 masses, and is encountering the primary disk at about 100 gravitational radii from the center. This is potentially, as we also saw the previous presentation, and people are finding more and more evidences, these are potentially precursors to extreme and intermediate mass creation spirals that people can potentially observe with LISA. Also, in this case, we calculated the expected gravitational wave signal. However, if you consider the system as it is now, and you consider the two separated black holes, basically the signal is too weak to be detected with LISA. But basically, with LST, we want to find more and more of these objects. So after we published in the paper, more questions kind of came up. Variability. How common are quasi periodicity in supermassive black hole systems? I remember when I studied agents at the university, basically it was a blasphemy to say something like that. And in reality, we are finding more and more evidence. Are there multiple objects orbiting supermassive black hole? Not just one, but you can have more objects which are embedded in accretion disks around supermassive black. What is the origin of the continuum? In particular, the black body continuum in these cases is not consistent with a standard accretion disk. And also the hot corona, this object and several others, they totally miss the hot corona that produces the power law in Seyfert galaxies, for instance. The origin of the outflows, the modeling of the accretion and ejection physics, which was done for single black holes, is probably not exactly the same. I include more objects, and also in the future, high cadence, long-term optical and X-ray observations could actually show us. I would expect that in a few years we might be able to do that to find really precursors to MRIs and IMRIs, and also are these transient repeating supermassive black holes sources of gravitational waves? What about persistent agents? Potentially, within the noise of the stochastic accretion activity, there might be secondary objects which will show up in gravitational waves. But electromagnetic radiation, basically, they are totally swamped by the background emission. To conclude, LST, why is going to be revolutionary? So for recurrent nuclear transients that we are starting to observe, basically we are expected to have thousands of transients per night with LSD. So it will be very, very tough to decide which one would be the one to actually follow up. Time resolved light curves with a cadence of days or to up to years will basically allow us to monitor this object and find more evidence for this periodicity. Binary supermassive black holes, we have seen evidence also in the previous presentation. EMRIs, IMRIs. So basically, through Rubin LST, it is expected that flare and quasi signals will be observed in accreting objects, and tens to hundreds of spirals might be detected per year. So basically, we are entering a regime like people were in the gravitational wave community just before switching on the detectors. And to end, multi-wavelength and multi-messenger synergies, of course, coordinated and follow-up X-ray, optical, radio, and gravitational wave observations will be the key to fully understand the mechanism of accretion and mergers on supermassive black holes. Thank you.
Questions? Sorry if I missed something, but you said that this object doesn't have X-rays, but at the same time you showed the nicer thing.
This object has X-ray. Probably there was a little bit of confusion with the previous talk. It has,
but in the list you said that these objects don't have a corona.
they don't have corona, but so the corona is the one that in the X-rays basically gives you the power law continuum that goes up to the hard X-rays. The spectrum of this object at many TDEs is basically just a simple power law, and it drops here at about 1 keV. So basically, what is missing is the hotter inner corona that in Seyfert galaxies of typical AGN gives rise to the power law that goes up to hundreds of keV.
Right. So in the binary explanation, is the binary close enough for us to expect precession to be relevant?
It would have been nice in the movie, but I think you can see here also this here is the projection of the orbit of the secondary with respect to the primary that will be here, and there is some precession. We are already in a regime where you would see relativistic precession. That will, so we tested it, and basically it gives rise to the peaks not to be exactly periodic, but to be quasi-periodic. So it will enlarge the peak in the power spectrum, basically. And eventually, the peak will shift to higher and higher frequencies. If it was in a spiral, you would see a lot of this precession, and then uh, the the peak will be not anymore at 8.3 days, but it will shift quickly to shorter and shorter timescales. But here it seems to be relatively stable.
Okay, if there aren't other questions, we can move on our last talk of today. It is, yeah, thanks, Francesco. It is a talk online. Alexander Golvat, that we talk about determining the parameters of supermassive black holes. Okay. Okay, our speaker is not connected, so maybe we can move can move on. Now it is the discussion time. So if you have questions or issues you want to raise or discuss, so this is the moment. About the talk of today, or general questions or comments.
Just really to kick things off, there was a conference in Sexton last week, and most people were pretty keen on these massive seeds. So supermassive black holes starting at 10 to the 6. And so it got me thinking, well, what about your intermediate mass black holes, say 10 to the 3, 10 to the 4? What are the formation mechanisms for them? I've got population 3 stars. But is that it? Are there other alternatives for forming the intermediate mass black holes?
Okay, very good point. Who would like to try to give an answer?
It was strange for us to see the evidence for a potential intermediate mass black hole orbiting a supermassive black hole, but that's probably also the kind of environment we'll try to investigate, because in order to form an intermediate mass black hole, you can also have it through either accretion. Imagine you have an AGN and a smaller black hole which is in a stable orbit. Both of them will accrete. So eventually we will end up with supermassive black hole plus intermediate mass black hole. Or you can also have globular clusters falling into the central region of galaxies, and that will provide a lot of confusion because you have a lot of objects. At the same time, the closer you get to the central regions, will become more and more compact, and eventually more mergers. And potentially, you would expect to have more intermediate mass black holes close to the galactic region. But I mean, these are ideas that we got when we were discussing about the possibility of indeed observing an intermediate mass black hole in that environment, so close to supermassive one.
Some other comments?
Actually, I have a question for theorists. So often we expect a flare from when you are close to a merger of two supermassive black holes. But potentially simulations, I think, also show that you might end up with a deep in. So basically, if we are looking for objects which are flaring, we might look for objects which are not the best ones to find supermassive black hole mergers, but we should look for kind of stable objects that will go to low luminosity um, event. Let's say, I don't know. It's because from your simulations, the central regions really looked kind of void of matter.
Yeah, so there's many studies that have predicted that situation, right? And you have two reasons. One of them is that the binary will empty, we will create an empty region, a cavity, um, and also that once gravitational waves take over, um, the binary will shrink faster and faster, and the disk cannot follow it. The viscous evolution will be slower than the gravitational wave driven decay of the binary. So you could expect the binary to form the binary to merge in a vacuum, and then you would have to wait a bit for a flare to occur. But yeah, that also is in a highly idealized case. So you could, at the same time, have a persistent circumprimary disk. So a disk that is around the main black hole that survives stays bound even while the secondary is plunging in. So I don't think there's like clear predictions at this stage. So no answer from me yet.
It's a different topic, but it's more or less like question because how much morphologies will let us know, figure out, okay, how fast two black holes if they merge, right? Getting into the center of the post-merger potential well, and if it, depending on the mass ratio. Currently, the system we are talking about mostly based on, for example, the shallow, the optical or the near-IL survey. Of course, there's an exception like the Subaru, for example. Do we have any examples to get a rough idea? Okay, are these all this extreme variability potentially due to two supermassive black hole interacting depending on the mass ratio? Could also relate with the overall galaxy morphology, which is suggests that there is got to be the hint of the post-merger, and roughly the time scale is more or less like it makes sense us to convince ourselves that okay, two things are actually getting into the center of the potential well. I mean, the LSST with the the depth of the LSST certainly will be better than the current optical near survey. But before we get to that point, can anyone comment if we have some deep near IL or the optical observations of those systems have some signature of the interaction or some.
I can try to give you a sense of the time scales. First of all, in general, the time scales from like the galaxy merger to down to subparsec separations are very uncertain. I would say, based on the modeling of the background, which is also uncertain and has a lot of free parameters, one of the conclusions is that you need to merge the black holes in less than 3 gigayears. Otherwise, you cannot produce the level of the background that we observe. So maybe that's one data point. Now, this is a very long time, and typically the features of the merger, like tidal tails and all these other things, dissipate much faster. So by the time we get to observe them like quasars with periodic variability or something like that, I would expect that the features will have disappeared. There is a new idea that maybe there is a signature, not necessarily morphological in terms I take an image, but like if you look at the stellar orbits and the kinematics, IFU or something like that, maybe that signature lasts longer. So if you look at the stellar distribution in the center, maybe that will be more perturbed, but not like the morphology of the galaxy.
My question, or like just a hint for discussion, going back to Francesco's talk, when it was mentioned that this AGN has a thermal spectrum, no power law. From my point of view, I come from the X-ray binary community. Almost all X-ray binaries lose their corona and power law component when they get above a few percent Eddington. So corona disappears and the jet is quenched. That's the X-ray binary side, stellar mass black holes. For AGN, although I'm not an expert, I know it's not as common. So it takes some special conditions for an AGN to lose its corona, even when it's more than a few percent Eddington. So I just wanted to ask if you have any comments or maybe there is a threshold in the mass of the black hole between the lightweight ones that can lose their corona so easily and the heavyweight ones. Did the lightweight ones lose their corona because the standard disk has enough photons to cool down the electrons in the corona, but AGN don't seem able to do that. Any comments?
Just before the microphone returns, AGN do have a special location at the center of galaxies where gas can end up pooling, whereas your X-ray binaries, they might be in the outskirts. Well, they are in the outskirts, so there's that environmental difference which might be at play.
Yeah, so basically, there is evidence that when you increase the antidote ratio for supermassive black holes, you end up with stronger black body emission, that kind of component similar to there, and you end up with a weaker hard X-ray corona. So probably when the luminosity is so high, you end up cooling too efficiently the inner corona, and basically you don't have much hot electrons there. There are some objects which are X-ray weak quasars that over time, I mean, they behave normally and then they become very X-ray weak. But the optical is basically constant. So in that case, it's still not clear if it is due to some perturbation in the accretion flow or something different. So it's still, I would say that the AGN community is still a very open issue.
I have a very different question, and it has to do with like the detection of AGN in LSST. So say in a year we start 6 months down the line we have the first data release. When do we expect to have the first catalog of AGN, and who is going to produce that? Is that, I don't know, is that an obvious question? Is there an answer?
One of the points that were brought up in at least in the Photosi AGN, we were putting some letter of recommendation. We said that one of the first things that we could do is just comparing Photosis for objects that were Galaxy or AGN, and depending on the difference at the cross square, that will give you already something. Then you have all the methods that have been developed until now, and when you have the first catalog, then you're going to cross match it with any possible AGN sample that has been already done. But there will be some time before that you are able to make an LSST based selection of candidates AGN. At the beginning, you only do LSST photometry for AGN that you already know. What exactly? Exactly. Rosita, Rosat, Quaya, everything that you know. Because you needed to know the data, you needed to be aware of the property before you were able to create new candidates. Unless you're using variability or other things that already been improved by the variability team.
When are we going to get to the 10 million quasars? Is it like 5 years down? Like the end of the survey?
Gradual. And you're going to improve on the method as soon as you learn more about the system. You're going to use more data for selecting the objects. I will show something on Thursday. There is plenty beyond photometry, total photometry that can be used. But we needed to train and have some data. So minimum, you need to have the first catalog based on LSST. And then on that, you start to flag what you think the energy based on LSST data.
Now, that's a very good point. That, in fact, what I was advocating is that we have to coordinate to some extent, because, of course, it's a general interest. Each one of us has a selection method. Many will overlap. Many of the data we have access to are publicly available. So we will, ZTF, everybody is working on ZTF data. And there will be, of course, multiple AGN catalogs, depending on the application, what you're searching for, looking for. But I think this is what our collaboration should do. So at least, have a general idea of how we're going to proceed, who is interested in doing that, what, and at large, there will be ample space, but we don't want to end up, the first data is all jumping, trying to do exactly the same stuff, with the same methods, because then somebody's going to release a code and we all use the same code. This is exactly why we should be here and think about something common.
In multi-wavelengths cover topic, because before it's true that we have to organize for writing proposal for when the data will come, blah, blah, blah. But we have tons of AGN that we already know, and we can already organize who is doing what for the rest, so that we can really collaborate and coordinate. So this is also multi-wavelengths of stuff that we already know. So I think that we can coordinate in that working group who does what is the priority, and all these kind of things.
So thanks for this nice discussion, and to all the speakers. To be very quick. Okay.
Right. Just a really quick comment. I think there's, like, what we're doing for the AGN variability subgroup. There's a lot of things that are common, right, between different science interests for variability. But I think it's the same applies to all different subgroups, selection, photo Z, right? There's a lot of work that we need to do for each subgroup, but there are some things that are central to everyone. I would recommend to form some cross subgroup task forces to tackle some of those challenges.
Now we have a few announcements from the organizers.
Thank you. We kindly invite tomorrow's speaker to upload their talk to the Drive folder. Thank you very much. This is the first. And the second is tomorrow we will go to the Martini Historical Factory. If you want to reach the tour, please, and you haven't said now already, please tell us now, because we have to organize everything and we have to know who is coming. Thank you very much. Okay.